Actually, the thing is that your golden section search technique is not that much efficient because it will take many iterations to converse and need more function evaluations because at every stage you have to compare your function values so that you will be gradually reaching to the optimum point. Another improvement of the technique is parabolic interpolation. Although the interpolation term is actually, I deferred this chapter because of this thing. The reason is that the interpolation and least square curve fitting are there in chapter 17 and 18. So for this reason, actually, after having our interpolation related thing with us, then we can easily understand the concept of interpolation as applied to finding the maximum or minimum values. It can be easily observed that at the point of maximum values or minimum values, you see this figure 13.6. You see that we can easily observe that a parabolic curve can best fit the region over which, for example, we are searching for the maximum. So if we have, okay, if we have, for example, a function that is what you true function that is by the solid curve, and our dotted curve is the parabolic function. That parabolic function can be represented by what if we have, for example, 3 points available with us, then by using these 3 points, say this is your x0, then in 1 point, this is your x1, the other point, this is your x3. Using these 3 points, can we find a polynomial, for example, say fx is equal to, you have seen this thing earlier, isn't it?
Yes,
That
sir.
a parabolic curve can be something like this, b0 plus b1 into x minus x, x1 minus x0, something like this. Can you remember this thing?
Yes, sir.
bt into x1 minus x0 into x2 minus x1, something like this. If we have our curve are with x, not x, x1, okay, this is x minus x0, x minus x1, x minus x2, something like this. Or even the equation can be easily represented as a0 plus a1 into x plus a2 into x square. Is it not the curve of a parabolic interpolated curve?
Yes, sir.
Then if we, how many constants we have?
Sir, 3 constants.
We have 3 constants. Then how many points we will need to find them?
Sir, at least 3.
At least 3 points will be, because if we, for example, put the point x1 there, then we'll have an equation. If we put the point x2 there, we'll have an equation. If we put the point x0 there, x1 there, and x2 there, we will find another equation, isn't it? If we solve these 3 equations simultaneously, not 0 actually, this is what the equation, okay? It is not 0, okay? You replace your x by x0, replace your x by x1, replace your x by x2. Then you will have 3 simultaneous equations. You can solve them to find the value of the constant a0 through a2, so that an equation of a parabolic interpolation curve will be available with us that can be best approximated in the region over which your maximum value exists. You see that this is say the dotted curve. Then what will be our next strategy? If we know the equation of the dotted curve, and your dotted curve is a fair approximation of your solid curve within that region, then what can we do? We can replace, for example, for the time being, our actual curve by the parabolic function, isn't it?
Yes, sir.
But this is an iterative process, of course, because Should be applied in many times in order to obtain the true maximum or optimum. Then what is our strategy? If we have a function parabolic fx with us, then we can easily differentiate it with respect to us and set it equal to 0 to find a value of x. Dash x will correspond to, say, the maximum value of this point, isn't it?
Yes, sir.
And that is another new point you are obtaining. Say this point is x3. Now we can easily compare that whether we are reaching at the maximum value at x3 or not by putting this x3 into the real function, isn't it?
Yes, sir.
Then we can say that no, if it is not the maximum value, then what you can do again, you can replace, you can just examine that which region or which point you have to discard. If we say that our maximum value will be lying between this among these 3 points, then we can easily discard this one. Then again we can repeat the process by using these 3 values where your x0 will be replaced by x1 and your x1 will be replaced by x2 and your x2 will be replaced by x3. In this way, we will have another parabolic interpolation. Then this interpolation can again be repeated to find the value, another point, new point, that will be the final approximation to the other. In this way, we can go. This is also an iterative process, but interpolation will be applicable at each of your point. Now, we have a formula already with us because the constant a0 through a1 should be determined. So if we determine the constant a0 through a1, a2 by using our equation that we have shown earlier and differentiate it and set it equal to 0, then we will find a new point x3, that is our equation 13.3. The designations of the points are in accordance with the figure that is there in your case, and the rest of the process of I have already discussed. And this is applied to this example. The same example has been solved for golden section search. Then you can have a look there. You will see gradually that we approximated 3 point, assume 3 point first x0, x1, x3. Function values are there. Then x3 point is evaluated using parabolic interpolation. Then again, a value is calculated here. And if we compare this value with the value that we assumed at the initial point, we can easily discard 1 point. Then the rest 3 points can be used to again repeat that process. So in this way, if we go there, you will find that after a few iterations, you will obtain the optimum value. To test whether we are reaching at the optimum or not, just you check the differentiation or the derivative of your function. Real function, where your derivative becomes 0, then you are reaching at the, by which point? Either maximum or
Minimum point.
minimum point. Okay, so this is the technique actually we can use there. Now, another very efficient and widely used technique is the other techniques that we described. They are actually semi-numerical type. But here you see that this is actually a truly numerical method that widely used. Why we need this actually, that I discussed probably in my first class in this topic, that if we have, our objective is what? We have to derive 2 conditions. One is necessary, another is sufficient. The thing is that we have to take the first thing is what? If we have an objective function fx, 1-dimensional, then we have to just set the derivative equal to 0, isn't it? To find the minimizer or maximizer x. Now, if you want to do that, then this is a new function actually. If this is a new function gx is equal to f prime x, the derivative of fx with respect to it, and that is equal to 0 at that stationary point. Now, with respect to gx, is it not a root finding type problem?
Yes, sir.
Because our objective is what? We need to find the value of x at which your gx would be equal to 0. That is similar to your root finding type problem. But then any root finding algorithm can be applied there. So Newton method is one of the best and efficient method with some pitfalls, but still it is widely used. Then we can apply them. Okay, so this equation is the just simple replication of the general form of your Newton method. It is a gradient projection method. For this region, you have to evaluate the gradient or derivative. Then your new point will be equal to the whole point minus this ratio fx divided by fx. By here, if we want to apply it for the derivative of fx, gx, then we have to replace the thing. In our case, it will be equal to x I plus 1 is equal to xi minus gxi divided by g prime xi, isn't it?
Yes, sir.
Here in this case, use gx is equal to f prime x and g prime x will be equal to f double prime x. This is what the equation. So if we just go in this way, we can easily find our values where we can have our maximum or minimum. Then after having this thing with us, we can test for maxima or minima by the sufficient condition. Now in this example, what was this example? It was fx is equal to 2. Actually, the thing is that whenever you are doing something, as I have been, as I have discussed earlier, that nature of the function is to be guessed, okay, or understood first, that how the function is varying with the independent variable. If we have a function, let me share one thing to you, just to show you how. Sorry, let me stop. Our function was equal to what? 2 sine x.
Sir, are you sharing in whiteboard?
No, I am not sharing the whiteboard. I will be sharing an Excel sheet. But I have to calculate it first, then I will share.
Okay, sir.
Okay, now do you have your text with you probably? What our example was what? It is not 2 sine square 2. What is it? I am sharing this book, isn't it? Our example was this. Fx
Yes, sir.
is equal to 2 sine x divided by x square by 10,
By
isn't
10.
it? So if we, for example, if we plot this function, your function will be looking like this, isn't it? So within this range, if you want to find the maximum values, then you can easily say that your maximum value will be arising at a point. Actually, horizontal axis is not mentioned. It is actually in the 17th or 16th row. If we go there in the 17th or 16th row, you see that it is the value of your x is somewhere between x somewhere between 1.4 to 1.5, isn't it?
Yes, sir.
So this is what your maximum value, that you know that the real maximum will be occurring there. Now, if we want to apply our Newton algorithm there, what you need to do? You first say you have to take the derivative first, isn't it? Our objective is if you want to find the point where your function will have maximum, then you have to take the derivative dx is equal to 0, isn't it?
Yes, sir.
If this could be solved easily, analytically, then we do not need any numerical technique, isn't it? In this case, what is that derivative? Is it not that derivative?
Yes, sir.
If it is U derivative, I think it is a transcendental equation. That equation contains sine cosine functions as well as linear function x, isn't it? So this is not that easy to be solved analytically. Now, our objective is what? We have to solve this. This is UGX. And if we further take the derivative, this is UG prime x, isn't it?
Yes, sir.
So then if your initial gauge is there, x0 equal to 2.5, then our recursive iterative algorithm would be equal to what? We need our second point I plus 1 with your initial value xi is given minus you have to calculate the value of g at xi. So this will be equal to 2 into cosine xi minus xi divided by 5. Okay, and divided by minus
2
2
sin x
into sine xi minus 1
1
by
by
5,
5.
isn't it? So any function can be there depending on the type. But here in this case, you see, if that derivative is not obtainable by analytical technique, then which alternative can we apply here? Because in Newton's technique, a similar method we studied where your derivative calculation becomes complicated or even sometimes not possible analytically. Can you remember the name of the technique?
So second method.
Yes, it was your second method. In this case, you need the two function values just by using divided difference type formula to approximate the derivative. Okay. So you see, then our next value x1 would be equal to what? Because we start with first I equal to 0 value is given there, then our x1 value would be equal to what? X1 value would be equal to x0 minus you replace your xi by x0 there in this equation. Okay. Then you will have your first value of x1 with you. Let me erase it, otherwise it will be overlaid and you cannot see the actually the things are already there. Okay, if you redo the thing, you will understand it very easily. This is an old topic. Okay, so that the first equation is the equation already we have written. In that equation, you replace your xi by x0 to find your x1. Your x1 is equal to 0.995. And you evaluate the function values there, and that function value is actually not the maximum. Then you have to go further to find your second value. You can easily then calculate your second value. Actually, this is not 1, this should be equal to 2, isn't it? You understand which one would be 2? This should be equal to x2.
Oh, yes, sir.
Okay, so in this way, if we proceed with, when we have to stop? We have to stop wherever you will find that your fx prime or equivalently gx would be equal to 0, isn't it?
Yes, sir.
If it is not equal to 0 or it might take longer time to proceed with, then we have to have some other criteria of stopping. Okay, let me just hold for a second because Okay, come back. Sorry. Then what is our stopping criteria?
Sir, relative error.
Relative error can be used there if your function is available, or the absolute criteria is actually we can easily guess that whenever we are reaching our maximum or minimum, where your gx value would be equal to 0, isn't it? That means slope will be equal to 0. So you can see that your f slope gx is equivalently equal to f prime x, and your f prime x is 0 after few iteration. Okay, when you see whenever your function will not be diverging and you choose your initial value properly, the Newton method is actually quickly converges. So this is your Newton's technique. Another technique is called Brent method. We will not discuss about it. You can have a look there just to find how this can be applied. Okay, so at this point, actually, in our case, in our electrical engineering cases, we have few problems or few types of problem that is one dimensional, but in most of the cases, our problem will be of multi-dimensional type. For this region, I will also give you some flavor how we can deal and how can formulate our multi-dimensional one. Okay, in this problem side, you see some very generalized problem. Okay, you can start with any problem. For example, fx is equal to minus x square plus 8x minus 12. If we have this function with us, you can easily find a gauge that how your function will be reaching maximum. Okay, but it can also be determined analytically. Can we determine analytically?
Yes, sir.
We can easily determine analytically. Then we can prove it by our numerical method that things are working. But if you want to go to problem 13.2, you see that that is not that simple, isn't it? So in this case, what you can do, if you have your Excel or other programs with you, you can easily plot it. Then you will find the approximate region over which your root may exist, maximum value may exist. Then you can apply any one of the algorithm there. Okay. So try to apply some algorithm there and find something. Okay. I will be discussing something practical that will help you how to formulate your problem. Okay. Let me share whiteboard. How a problem can be, let us consider a simple problem. Then because your power, maximum power transfer theorem is also a problem of this type, isn't it?
Yes, sir.
But you have already seen that your power PRL for a simple network is equal to what? It is equal to your VTH squared divided by RL plus RTH squared multiplied by RL, isn't it?
Yes, sir.
You can verify this thing if your values of RL and other things will be available to you. RL is variable, then we can easily apply any one of the algorithms that we learn for first order cases to find the maximum value, the value of RL where power becomes maximum. Now it is one dimensional in this case, isn't it? But this problem can be converted into multi-dimensional type. How, I will discuss it a bit later, because in RTH actually we may have our many things involved. For example, as it is the equivalent of a Thevenin equivalent resistance of what? Of a network, isn't it?
Yes, sir.
If your network contains some other variables, then those variables will be coming with RTH. If those variables will be coming with RTH, that will also affect RL, isn't it? At which your power will be maximum. For this reason, you will see that your power RL would be power P would become the function of many variables. Okay, we'll discuss later. Okay. Similarly, consider another very practical problem. Okay, a design of a simple gutter. Okay, this is actually used to drain water or something like this, a trapezoidal shaped channel, something like this. Okay. If we have the channel, for example, with side equal to A, this side equal to A, that side equal to A. Now you have been asked to find an angle, for example. What is that angle? This is a problem I have found in many books, or even when a website is there in numerical method, you can have a look there. Many practical problems are discussed. Internet you are using, okay? Try to use it in a very productive way, not for cheating or other purposes. Then you will find many things there and that will enrich your understanding. Every day I am trying to learn something new. Otherwise I will not survive. Because I was at your stage about more than 40 years ago, where things were not something like that, what you are saying. But in order to get myself aligned with you, I have to update myself every day. Otherwise, I will be ruined. So this is what you theta. Now your question can be something like this, okay? You find the value of theta, optimum value of theta, so that the area of your channel will be maximum. The constraint here is given. What are the constraint? The sides are given, isn't it?
Yes, sir.
In this case, what will be the range of another constraint that theta should be from where to where? What will be the range of your valid range of your theta?
Sir, 0 to 90.
0 to 90 or 90 degree. 0 to pi by 2 radian, okay? While you are calculating your trigonometric quantities that involves angle, be careful about the unit, okay? Now, can you tell me what is the area? Let's say this area is A. That area equal to what? What is that area? What is the length of this side? This side equal to
A sin theta.
A sin theta. Fine, very good. If it is A sin theta, this is it not A cos theta?
Yes, sir.
Then the area would be equal to area of this square, not a square, rectangle. That area will be equal to A multiplied by A sin theta plus 2 into area of the triangles, half into A sin theta, the height, multiplied by A cos theta, the base, is it not?
Yes, sir.
And that will be equal to what? A square sin theta plus A square sin theta cos theta, isn't it?
Yes, sir.
Or you can write in a way that A square sin theta 1 plus cos theta. Now, if your problem will be of two-dimensional, then your A will be the function of A and theta, isn't it?
Yes, sir.
Then it becomes a two-dimensional problem. But if we fix our A, then this will be equal to the function of theta only, isn't it?
Yes,
So
sir.
if it is the function of theta, and your A values will be given, of course, given, then you can plot this function in Excel to find where your maximum value can occur. Then you can use your golden search technique there, or even Newton. Let us apply Newton's technique now. okay, in this equation with a given value of what a. If we have our a equal to say 4 centimeter, if a is 4 centimeter, then a theta equal to what? 16 sin theta into 1
1
plus
plus
cos.
cos theta.
Very good. Can we write this in this way rather than expressing this in this way for our better understanding? See, 16 sin theta plus, can we write what is the equation for cos theta sin theta? 2 into cos theta sin theta equal to sin 2 theta.
Yes, sir.
Is it okay?
Yes, sir.
So in this way, how can we write it? It would be equal to 8 sin 2 theta.
Yes, sir. Sin 2 theta.
Okay. Now what we need to do? We have to find our first derivative. Would be equal to what?
16 cos theta plus
Plus
sin 2 theta. So 16, it would be 16 cos theta, cos 2 theta.
okay.
Yes, sir.
And a double prime theta equal to
Minus 16 sin theta. Minus 32 cos, sorry, sin 2 theta.
fine. Your values are already with you. Now let us start with theta equal to 0 degree. Say what happens. This is what your first iterative value, okay? Theta 0. Then theta 1 would be equal to what using Newton? Theta 1 would be equal to theta 0 minus value of your a prime at theta 0 divided by value of your a double prime at theta 0, isn't it?
Yes, sir.
And that is equal to what? 0 degree. 0, let us consider radian, not degree. Okay, 0 degree, 0 radian minus 16 into cosine 0 radian plus 16. This is also cosine.
Yes, sir.
Then it will also be 16 into cosine 2 into 0. Okay, divided by. Can it be calculated at this point?
No, sir. It will be infinity.
Is it not? That means it will diverge actually. For this region, what you need to do, you have to choose a value other than 0. That's why try to solve it with another value of theta that will be detectable and compare the result. Okay. What will be the maximum value of theta that will give you the area maximum. Okay. Now I am what I have told you that how to convert it into a 2-dimensional. Actually, we have already dealt with 2-dimensional problem earlier in least square technique. Actually, the thing is that what was our basis? Our basis was actually Taylor series, isn't it?
Yes, sir.
We express this function into Taylor series in the vicinity of the maximizer or minimizer. Now, if we have our 2-dimensional function, fx, say function fx and fy, then if we want to, then what will happen then? In this case, you will have a value of x asterisk as well as y asterisk, where your function will be maximum or minimum. Then if we perturb, for example, this value to some direction delta plus z plus minus delta or y delta x and say y plus minus delta y. Then we can easily, this is your value of x, this is your value of y. Then this function can be approximated by a two-dimensional Newton's two-dimensional Taylor series, isn't it?
Yes, sir.
And that will be equal to what? It will be equal to f x asterisk plus f y asterisk plus your step size, for example, del x into f prime at what value? F asterisk
Uh,
plus, this should be actually d by dx. Let us write in this way, d by df by dx at x equal to x asterisk plus d delta y into df by dy at x equal to x
Sir, y
asterisk.
equals to y asterisk.
Y equal to y asterisk. Exactly. So in this way, you can proceed with your higher derivative. Okay. Now the question comes, actually, you see, whenever we are setting to our maximization or minimization problem, then these derivatives should be equal to 0.
Yes, sir.
Actually, those derivatives are multidimensional cases written in this way. Okay, we usually use a vector there with a bold value, say capital value x. That x is actually an array of functions. Okay, it can be x1, x2 up to xn, n dimensional can be there. Okay, in this case, this value we can easily write as f capital asterisk, something like this. Okay, it will be a vector. Then in this case, what you need to do, this derivative will take the shape of a function del fx with a value multiplied by what? X minus x0 or something like s asterisk. Okay, that is what the step size. Then another issue, and this must be equal to, because these two vectors are what? Are they, if they are vector and they are column type vector, can we multiply them in this way? Hey, what is the condition for matrix multiplication? If we have our two column vectors or row, can we multiply them
No, sir.
in this way? We have to transpose one, okay? So
Yes.
that your transpose value should be something like this. It will be converted into a column or a row, then it is satisfied. So it will be transposed, okay? So in this way, we can go. So a multidimensional problem, actually, here you see that a transpose is needed there. The region of the many variables are there. So in this case, what will happen? You will see that we are dealing with a quantity del ft. That is actually the derivatives are involved there. Okay, this is actually called gradient. Okay, what have you seen there in your electromagnetic field, that your E is equal to negative gradient of voltage, isn't it?
Yes, sir.
So in this case, is it not a derivative in a space, but it is vector. So this must be a vector. In general, when we are in the geometrical way of handling this thing, your gradient must be a vector actually. So if it is a vector, you see that how many components are there in x, y, z? This is equal to d dx, v ax minus dv dy ay minus dv dz az in general, isn't it?
Yes, sir.
And why partial derivative is needed? The reason is that your v is the function of x, y, and
Z.
z. So in this way, you see that if you want to write the derivative, actually this gradient is actually a column vector. This is the derivative of your function, say with respect to x1, derivative of your function with respect to x2, and go all the way, derivative of your function with respect to xn, okay? In this way, you will get your column vector, and that vector should be equal to 0 to find your maximizer or minimizer point. It is your the necessary condition. You got the thing?
Yes, sir.
In order to get the sufficient condition, actually, we need the second derivative. Your second derivative of the multidimensional function is called Hessian. Okay, your Hessian can be calculated by differentiation your function with respect to x, with respect to x1, and with some, it becomes a matrix rather than a vector, okay? So your Hessian, because I am not going, because if we go to that detail, then it will be another topic, and I am not going there, just giving some introduction to you so that you can move ahead with it in your higher order courses where you will take some optimization courses for your master's program. Okay. So yeah, a two-dimensional cases, your Hessian can be something like this. If you have a function that is the function of x1 and x2 only, then your Hessian would be equal to a second derivative of f with respect to x1, x2, and we'll have a second derivative of function with respect to x1 and x2. Your second derivative of your function with respect to dx1, dx2, and your second derivative of your function with respect to dx2. This is what your Hessian. That natural Hessian will tell you whether you are reaching at a maximum or a minimum or a saddle point. In this case, actually, three options are there. One is called maximum. Your maxima, something like this, that it will have a maximum point, or it can have a minimum, but you may have a curve something like this. Okay, consider that you have a curve something like this, and that curve is a two-dimensional curve. Okay, many curves are there coming. Okay, and some other curves are also there coming. Okay, do you know what is surface plot in your MATLAB?
Yes, sir.
So yeah, you'll find some point there. Okay. Do you know what is called saddle?
No, sir.
No. Then when you are using, how many of you have, for example, ride cycle, bicycle? Bicycle seat is actually sometimes called saddle. Okay. Saddle is actually coming from the horse ride. If we have a horse, can you find the shape of a horseback?
Yes,
Is it
sir.
not something like this? So sometimes you see that your some cushion or something like this is made of leather is placed over, for example, this bag, and over which you sit. Okay, you cannot sit directly to the back of your horse. And that curve, actually, if you go to this back, you see that your horse curve is something like this. Okay, if you just go one contour, it will be looking like this. Okay, this is what your body. Then this point, actually, if we consider this curve, then this point is minimum. But if we consider the curve in the other way, I will be showing this thing to you because I have some slide, but I have to search it. Then this point is actually, with respect to this curve, this point is maximum. So as a result, this point is actually neither maximum nor minimum. and that type of point is called saddle point. So in your multidimensional optimization, you may have a maximizer point or a minimum point, and there can be some point where it is a saddle point. And that test can be identified by examining the nature of the Hessian. And again, you will need some higher order mathematical or matrix algebra or linear algebra. So actually, we have a matrix classified as definite, semi-definite, positive definite, semi-positive definite, negative definite, semi-negative definite. Have you learned about those things? When you have been introduced with eigenvalue? So I will not be going there because this will again bring another discipline, but just for your introduction. Okay, if we have our all eigenvalues positive, then your matrix is a positive definite and we will be reaching at minimizer. If some eigenvalues are 0, others are positive, we will be going to a local minimizer. And if all eigenvalues are negative, then we will be at a maximum point. And if some eigenvalues are negative, other are not 0, then we will be a local maximum. If your eigenvalues are positive as well as negative, then we are in a saddle point. Or there exists another criteria of defining the definiteness of the matrix by examining the nature of the principal cofactor. Okay, then how to then find, in this case, then what will happen then? We will have two things. One is your Hessian, another is your gradient. Okay, by using that gradient and Hessian, you can easily find where your function will have the maximum or minimum values for multidimensional cases. Okay, how to apply this thing? Because we have already applied this thing, but we did not, for example, refer the thing in this way. For example, consider your square case. I have a least square case, okay? Whenever we are approximating, for example, a function by a straight line a0 into a1x, a data set was there. That data set was, say, x value was there, y value was there, and we feed this data set by using a straight line. Is it not the problem of our linear regression that we studied in least square curve fitting? In this case, what have we done? That we calculate the error at each point, then we squared the error and we minimize the error, isn't it?
Yes, sir.
And that minimization technique was something like this. We calculate the error in this way. Our actual value of yi is given. Our approximate value of yi is given. This is what you error. We square the error and sum the error. And that error function you can call say s. Then we take the derivative of s with respect to, and you see that if we go calculate the thing in this way, you will have a polynomial function x, and that will be the function of a0 and ay. Is it not?
Yes, sir.
It is a function of a0 and ay. If it is a function of a0 and y, our objective is what? We have to minimize this error. If we want to minimize this error, is it not an optimization problem?
Yes, sir.
Then in this case, is it a multidimensional or one-dimensional?
So multidimensional.
What are the design variables here?
So A0, A1.
A0 and A1, very good. Then what you have to calculate according to our steps, what we follow in optimization, what you need to do. You have to calculate the gradient, isn't it? Your gradient is nothing. You take the derivative of x with respect to A1 first, A0 first, and take the derivative of s with respect to A1, isn't it?
Yes, sir.
Set them equal to 0. then you will obtain two simultaneous equations to find the value of A0 and A1. That is what your maximization or minimization problem in terms of your optimization. Okay, so this is the case. Just I will be concluding after one mentioning something. Okay, in your power problem, maximum power theorem. Okay, if we have a network, very simple. Say this is R1, this is R2, and we have this resistance there. It is something like that. A potential divider is designed. This value is E to feed your RL. Is it not? Is it not a potential divider?
Yes, sir.
With respect to if we separate this network. Now the question is, if we keep the network in this way and find the value of RL, but we do not know the value of R1 and R2, then your maximum power P, that means power at load P, will now be the function of R1, R2, and RL, isn't it? Or you can keep one value constant. Say this value is kept constant, then it will be a function of P into R2 RL, isn't it?
Yes, sir.
Okay, now I am giving one self assignment to you. Just you solve this problem for any value of, consider that E equal to 10 volt. Your R1 is equal to say 5 ohm, but R2 value is not given, and RL is ranging from 0 to say 20 ohm. So with this range of RL, then you find the point where you will receive the maximum value, and at this point, what will be the value of your RL? What will be the value of your R2? And how to find it? You just find the expression of power, then you take the derivative with respect to dR2, and you take the derivative of power with respect to dRL, set it equal to 0. These two equations will give you the value of RL and R2. That will be the values of your resistance where your power will be maximum. Let us try it. Okay.
Okay, sir.
That's it. That's it from my part today.